Alright, in this lesson we will be looking at certain characteristics of a polynomial function, including the solutions or the roots of the polynomial functions, the number of possible imaginary roots, and the number of possible real roots, the number of possible rational roots. So starting with the number of roots, the way that we find the number of roots or complex roots, it's always the degree. The number of roots is always equal to the degree of the polynomial. So if we have the following polynomial, the degree is 5. It's the highest exponent for all the terms in the polynomial. So the degree of this polynomial is 5, therefore there will be 5 roots, 5 complex roots. To find the number of imaginary roots, we need to remember that imaginary numbers always occur in pairs. So, since they always exist in pairs, the number of imaginary roots will always be an even number less than or equal to the degree of the polynomial. So with that same polynomial, since the degree is 5, there will either be 0, 2, or 4 imaginary roots. And roots are either going to be imaginary or real. Those are the two possibilities. So to find the number of real roots, we just subtract the degree from the possible, the degree minus the possible number of imaginary roots. So starting with the degree for the same polynomial, the degree is 5. So we had 0, 2, or 4 imaginary roots. So if we subtract 5 minus the 4, we get 1. 5 minus the 2, we get 3. And then 5 minus 0, we get 5. So there's 1, 3, or 5 possible real roots. And then lastly, the number of rational roots. If we're going to use the rational root theorem to determine the number of rational roots. And remember, a rational number is generally any number that you can write as a fraction. So to find all the rational roots, you need to first take the constant term, find all the factors of the constant term, and then take the coefficient for the lead term, and you're going to divide the factors of the constant term by all the factors of the coefficient of the lead, the factors of the lead coefficient. For example, using the same polynomial function, the constant term is 27. The lead coefficient is 1. So we need to find all the factors of 27 and 1. So 27, the smallest factor of 27 is 1. The biggest is 27. Another factor of 27 is 3, plus and minus, and 9, plus and minus. The only factors of 1 are plus and minus 1. Alright, so the possible rational roots are positive and negative 1, positive and negative 3, positive and negative 9, and positive and negative 27. Alright, now lastly, to find the roots of any polynomial, there will be a series of steps that you need to follow. What I would suggest doing first to find the rational roots, I would suggest using either a graphing calculator or the Desmos app online. Plug in the equation, and where that graph crosses the x-axis, it is going to, where the graph crosses the x-axis will give you the rational zeros for that function, the rational roots for that function. So I plugged this function into the Desmos calculator and saw that one of the rational roots is going to be 3, because I saw that the graph crossed the x-axis at x equals 3. So now I'm just going to use synthetic division to divide that 3 into the polynomial, and then that will give me a depressed equation. Alright, so following all the steps that we went through in synthetic division, we get the following depressed equation: x to the 4th power plus 10x squared plus 9. So now we can take that depressed equation, it's a 3-term depressed equation, so now we can use substitution to find the factors. So first thing we want to do is set u equal to x squared, and then we're going to replace all the x squareds with u's. So x to the 4th is the same thing as u to the 2nd power. X to the 2nd power is the same thing as u. So we can rewrite that equation as u squared plus 10u plus 9 equals 0. And then we could just plug it into the quadratic formula, or we could have just factored. We could have just factored that polynomial, because it is factorable. Factors are x plus u plus 1 and u plus 9. So we could have found those factors by just using factoring. So since the factors of the roots for u, the solutions for u were -1 and -9, we can set both of those equal to what we let u equal. We let u equal x squared, so we're going to set -1 equal to x squared. So for the roots from that equation, we get x equals plus and minus I, since the square root of -1 is I. And when we set -9 equal to x squared, we get x equals plus and minus 3i, since the square root of -9 is 3i. Alright, next example, or our first example. First thing we want to find are the roots. The number of complex roots is the same as the number of roots. You can write any complex number as any real number. All complex numbers have two parts. It has a real part and it has an imaginary part. So if one of those parts is 0, if say the real part is 0, then you have an imaginary number. If the imaginary part is 0, then you have a real number. So the number of roots, or complex roots, is 4. Same as the degree for the polynomial. The number of imaginary roots is the number of the even numbers less than or equal to the degree of the polynomial. So we've got 0, 2, and 4. And the number of real roots is the difference in the degree and those possible imaginary roots. So if we subtract 4 minus 4, we get 0. 4 minus 2, we get 2. 4 minus 0, we get 4. So there will be 0, 2, or 4 real roots. And then to find all the rational roots, we're going to take the constant term, all the factors of the constant term, divided by all the factors of the coefficient of the lead term. Alright, so factors of 14 are positive and -1, positive and -2, positive and -7, positive and -14. And since the coefficient for the lead term is 1, when you divide each of those numbers by 1, you just get what you started off with. Alright, so we're going to do another u substitution. Since we have a three-term quadratic equation, we're going to let u equal x squared, so we can rewrite that equation as u squared plus 9 That should be a u. Let's fix that real quick. So I just want to change that to a u. All right. So u squared plus 9u plus 14 equals 0. That is factorable because 7 times 2 gives you 14, and when we add 7 and 2 we get 9. Alright, so we got u plus 2 and u plus 7 times u plus 7. So our values of u are -2 and -7, so we need to set each of those equal to x squared. When we set -2 equal to x squared, we get x equals positive and negative I root 2. And when we set the -7 equal to x squared, we get positive and negative I root 7. Alright, next example. Alright, we've got a pretty long polynomial. It's a degree of 8. So there's going to be 8 roots. 8 complex roots. The number of imaginary roots is, again, the even numbers less than or equal to 8. So we've got 0, 2, 4, 6, or 8. And then the real roots are the difference between the degree of the polynomial and the possible imaginary roots. So 8 minus 8 is 0. 8 minus 6 is 2. 8 minus 4 is 4. 8 minus 2 is 6. 8 minus 0 is 8. Now the rational roots. The constant term is 27, so we need to write out all the factors of 27 and then divide that by all the factors of our lead term. The factors of 4 are 1, 2, and 4. That gives us all these possible rational roots. So what I typically do is I start with, whenever you're listing the rational roots, try and list them in order from least to greatest. So the smallest numerator is 1, and you want to divide that by the biggest denominator to get the smallest number. And then we're going to leave we're going to go from the biggest denominator to the smallest denominator. We're going to do the opposite in the numerator. We're going to go from the smallest number in the numerator to the biggest number in the denominator. Alright, so we have 1 divided by 4. We have 1 divided by 2. We have, now we're going to skip the 1 and we're going to go to the next factor in the numerator, which is 3. 3 divided by 4. 3 divided by 2. And then again, we're going to skip the 1 in the denominator, go to the 9. 9 divided by 4, 9 divided by 2, and then the 27. 27 divided by 4, 27 divided by 2, and now we're going to go through all of the factors from left to right in the numerator and just rewrite them, because when we divide by 1, we're just going to get all those numbers in the numerator divided by 1, or just 1. We're just going to get all the numbers in the numerator. So plus and minus 1, 3, 9, and 27. Alright, so there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 24 different possible rational roots. Alright, so I actually plugged this into Desmos, and there are actually no rational roots. So we were actually given one of the roots, which is -4 plus the square root of 7. So we know that there is going to be a conjugate for that one. So there will also be a root of -4 minus root 7. So what I want to do, is find out what the equation would be if I took those two roots. Each one of the factors for a polynomial you can write as x minus the root. So I'm going to write each one of those as x minus the root, and multiply those two. First thing I have to do though to do that is to set the whole thing equal to x. And I set that equal to x. I get x plus 4 squared equals 7. And so x squared, writing out that equation, we get x squared plus 8x plus 16. Alright, so that is, now I want to subtract 7 from both sides. Alright, and that represents a depressed equation that I can now divide into that big polynomial. Alright, so we already have two roots, -4 plus root 7 and -4 minus root 7. So I'm going to take that polynomial and divide it into that depressed equation. I'm going to divide that into the polynomial. Since I know that that depressed equation is a factor of the polynomial, I'm just going to do long division step by step, making sure I'm being careful of the signs. I kind of speed through this. Alright, so eventually we get to we should get a factor, a remainder of 0, since x squared plus 8x plus 9 is a factor of that polynomial. We were supposed to get a remainder of 0, but now our quotient is another depressed equation that has 4 terms. And you should remember that whenever you have a 4-term expression or polynomial, you can usually factor it by grouping. So if we take a look at the first 2 terms, we can factor out a 4x to the 4th power. That will leave us with x squared plus 3. And then the second, the third, and the 4th term, I can factor out a -1. And in the parentheses, I have the same thing that's in the first set of parentheses. That's what we wanted. So both of these 2 terms now have a common factor of x squared plus 3 that I can factor out from those 2 terms. When I factor out the x squared plus 3, I'm left with 4x to the 4th power minus 1. Alright, so now I have 2 other expressions that I can, 2 factors now that I can set equal to 0. I set the x squared plus 3 equal to 0, and I get 2 more roots, which are plus and minus I root 3. And the final 4 roots I can get by setting the 4x fourth, the other factor, 4x to the 4th power minus 1, set that equal to 0, or factor it. You can factor it, you get 2x squared, we're going to get 2x squared plus and minus 1, set each one of those equal to 0. And we set the 2x squared plus 1 equal to 0, and 2x minus 1 equal to 0. We get x equals, x squared will equal -1/2, so when we take the square root, we get x equals plus and minus I root 2. I rationalize the denominator. And when we add 1 to both sides, divide both sides by 2, x squared is going to equal 1/2. So x will equal plus and minus the square root of 1/2, which once you rationalize the denominator, you'll get plus and minus the square root of 2 over 2. So we have our additional 6 roots on this slide.